In order to be able to model a tensor accelerator, one of the first things you need to be able to do is specify its workload. In this case, we want to be able to talk about what we might call the problem specification for the accelerator. So what is the tensor computation we're going to do? What I'm going to do is going to give a couple of examples of tensor computations and how we might represent those computations for specifying the problem or the workload that we want to model. So the first example I'm going to give is a tensor matrix multiplication. I'm sure many of you are familiar with this computation. In this case, we have two inputs, A and B. What I'm going to show you here is our conventional naming that you'll see periodically through these talks. The inputs are each two-dimensional tensors, and the input A has one dimension named M, and then another dimension named K. The input B shares the dimension K in its also two-dimensional tensor form and has another dimension N, and then M and N are the names of the dimension of the output. And as I'm sure many of you are familiar, an example of the computation is that you take a row of A and a column of B and do a dot product, which means you do an element-wise multiplication of each element in the row of A and the corresponding element in the row of B. You do all those element-wise multiplications, sum the results together, and that generates exactly one output in the output matrix. You then can move to the next column of the B matrix, the B tensor. Again, do a element-wise multiplication and sum, or the dot product, generate another output. You can then do that on for each of the additional rows, columns of B. You then move to the next row of A. Again, do a dot product against the first column of B and all the other columns of B, generating the second row of results in the output. Continue doing this for the rest of the matrix. I'm sure you're also familiar with common notation for that. I'm going to show you a loop nest and go over a little bit our notation for describing computation as a loop nest. What we see is a set of nested loops in each of the dimensions of the different matrices or tensors in the input. So we have M, N, and K. We're going to use a convention where small letters tend to be the index or the value of a in a dimension of a matrix. We're going to use this notation here of an open range between 0 and M, the number of elements in that range, and then there's a computation here where you do the dot product of A and B, creating each individual output. Now, something that's true of this representation is that it actually specified a computation order, and we would like to be a little bit agnostic to the order of the computation when we describe the problem. And so we will tend to use a notation which is often called Einsum notation, based on some specifications originally by Albert Einstein, where we write down this implied computation. We see Z of Mn, which means that we are going to create a result in Z for each of the indices M and N, each of the values that are legal for M and N. And what we're going to do is we're going to do multiplication of A, M, and K, B, K, and N. And what we see here is that M and N appear both in the input and output. So those tend to be referred to as uncontracted dimensions, because for every M and N value, we're going to get some value or multiple values of A and B and generate one value of the output. K, on the other hand, appears in the input side, but doesn't appear in the output. And that is because K is, as we know, going to be used for doing the dot product, and in Einsum notation that would be referred to as a contracted dimension. It means for the element corresponding values of k, we're going to do the dot product between the row and column of B. So what we've done now is describe sort of generically what the computation is. In addition to that generic specification of the problem, we actually need to talk about a particular instance of that problem. And for matrix multiply, the instance of the problem is going to be specified by concrete values for m, k, and n. So m is going to be the height of the input A and the output Z. For example, m might be 256. We're going to have to specify a concrete value for k, the width of input A and height of input B. For example, k equals 128. And n is going to be the width of input B and the output of Z, and it might have a concrete value of 67. So that's how we would specify precisely the problem of matrix multiply using the Einsum notation and its instance by specifying concrete values for m, k, and n. Another common tensor problem that we might want to express is tensor convolution. And here what we have is a set of filters and a set of input feature map, or input activations are sometimes called, and a set of output feature maps. What we're going to do is we're going to do a convolution of each of the planes of the input filter with each of the planes of the input feature map. And so here we gave an example of the end. So what happened was we're doing a convolution on this window of the input activations. We do a dot product, a two-dimensional dot product of the plane of the filter against this plane of the input. We then do that for each of the planes, add those results together to generate a result in one of the output planes of the output. This is a complicated computation, and it could be represented by this loop nest. And so what we have here are the for loops over these various dimensions. So we're going to generate an output for each of these dimensions. And for each of these dimensions, we're going to do a convolution. And so we're going to iterate over these dimensions and do the convolution operation. Again, we're doing a dot product. We're adding together a sum of element-wise multiplications. Again, that computation as expressed there actually expresses a specific order of computation, and accelerators might want to be able to do things in different orders. And so we can again use a more generic expression using the Einsum notation, where now the only difference here is that some of the indices are actually now computed generally using a very simple expression of various input index values in order to express the convolution. And so we have outputs NM, PQ, N and C. N appears in the output, and so is an uncontracted dimension, but C does not appear in the output, so it's going to be a contracted dimension. P appears in the output, but there is an R here, so that means we're going to do a contraction across R. Similarly, Q appears in the output, and S is a contracted dimension that doesn't appear in the output, but does appear in the other argument. So again, we have a way of abstractly representing the computation that we want to do for doing a deep learning style convolution That's the generic operation. What we again need is a specification of the instance, and in that case we have this big, secret decoder ring for all of the parameters for which we need constant values in order to be able to specify the input. And so what the tool is going to do is it's actually going to allow you to express in text the Einsum type expression, and then which generically says what your tensor computation is, and then the instance variables for all of the dimensions.